Okay, welcome back to chapter 19. We're going to discuss some reactions that aldehydes and ketones undergo, many of which you've had back in chapter 17, so I'll be able to kind of go through those pretty quickly. So let's take a look at section 19.3 on page 124. And here I'm going to describe some old-fashioned techniques for converting aldehydes into, in this case, carboxylic acids. So here again we're going from an aldehyde to carboxylic acid. So this is also an oxidation. A couple of specific examples. One of these includes the use of Jones reagent, okay, and the other includes Tollens reagent. Both of them give you the same results, but the conditions are quite different. So recall that if we had an aldehyde such as benzaldehyde, and we oxidize that, then we would get benzoic acid. Okay, so you can see that that's an oxidation because we've increased the density around that carbon with highly electronegative nuclei, or simply put, we added an oxygen. Now, Jones reagent, okay, Jones reagent is very, very harsh. Okay, here's what it is. Jones reagent consists of chromium 6 oxide at a very, very low pH. You have acetone, so on and so forth. And what this does, it generates chromic acid, which is a powerful oxidant. And realize this is chromium 6+, so it's very toxic, and that's one reason that this is no longer a favorable reagent, but it's very effective in producing carboxylic acids. A little more safe, I guess significantly more safe, is the use of Tollens reagent. Okay. Now, Tollens reagents are actually under basic conditions. Here we have silver oxide, ammonia dissolved in water, and ethanol. And the interesting thing about this case, we conduct an oxidation, but silver ends up being reduced to a silver metal. So this is how we make mirrors. Okay, you can take an aldehyde or some type of reducing sugar, mix in Tollens reagent, swirl it around, and the silver will plate itself out onto the glass. Henceforth, this would be a redox reaction whereby the organic substrate is oxidized, but the metal gets reduced from silver 1 to silver metal. So rather than write the names of the reagents, okay, we just put the names of the person who came up with them, Jones and Tollens, but in effect they give you the same results. Now, a little more contemporary would be the discussion under the heading of nucleophilic addition reactions of aldehydes and ketones. Now, you've actually had this back in chapter 17 when we discussed the Grignard reaction. We also discussed sodium borohydride reduction of aldehydes and ketones. But let's just talk about it in a little greater detail than we did even then. Now, you may remember, okay, I'm sure you do, that the carbon atom of the carbonyl functionality is electrophilic. And the reason for that, which you can tell by this illustration, is that because carbon has an electronegativity of 2.5, oxygen is 3.5. So there's a difference there in electronegativity, okay, of a full unit, okay? And so that means this bond is polar covalent, okay? So again, we use this phrase that the carbonyl bond is polarized, okay? It's polarized in the direction towards the oxygen. So we have a dipole, okay, that would run right through there. Now, when nucleophiles come into this sp2 carbon, they tend to come in at this angle. Right? Notice that the angle is not a right angle, it's not straight behind, it's pretty well defined, and it kind of depends on how big the nucleophile is, the nature of the nucleophile. But we go from an sp2 carbon here to an sp3 carbon, right? So in other words, we're now sp3, okay, an sp3 nuclei. So you added a nucleophile to that carbon. So this is what we're looking at. Now, the nucleophiles that we're going to examine, some of which you've seen before, okay, include the following. Let's just take a look at what they are as a reminder. One simple nucleophile that we have is a hydroxide. Okay, we realize that all nucleophiles have at least one lone pair, and the more potent ones tend to have negative charges. So hydroxide ion would be an example of that. Another is hydride. Okay, now hydride can come from a number of sources. You've seen sodium beryl hydride, you've seen lithium aluminum hydride, and earlier you saw DIBA, which is a diisobutyl aluminum hydride. And here's another one. Okay, this was a very potent. Of course, this would come from a Grignard reagent and other sources, mostly Grignard. This would be an example of a carbide, all right, carbide anion. And so sometimes in more contemporary jargon, we call that a carban ion. Carban ion. Okay, very potent nucleophile. And of course, we have the alkoxy or alkoxide species, which are simply the conjugate bases of alcohols. They can act as nucleophiles. And an important one in this chapter is this one here, is the cyanide. Okay, cyanide. We were going to use cyanide in the lab, you may remember, to make benzaldehyde into benzoin. Too bad that didn't work out, but nonetheless, it's a very potent nucleophile that we'll make use of in this chapter. Now, so these are examples of the charged nucleophiles. Notice they all have negative charges. They all have at least one lone pair. Okay, so they are the all of them are the conjugate bases of very weak acids. Now, the nucleophiles that are neutral, and the reason they can be nucleophilic is because they have lone pairs. Most of these have oxygen or nitrogen as a nucleophilic component. Would, of course, include things like water. Okay, goes without saying. And, of course, we have alcohols. Alcohols, of course, have an sp3 oxygen that bears two lone pairs. Ammonia. Ammonia is a gas, and we can generate it in situ, or we can bubble it in. And we have also amines. Okay, this is an amine. And the amine that I'm showing you here is actually a primary amine. More than likely that our group has to have carbon. But you can have secondary amines there as well, so on and so forth. So what do we know about all of these? What one thing do they all have in common? All of them are Lewis bases. Let me just write that up here. Lewis bases. Okay. And Lewis bases, by definition, are electron pair donors. And so they donate one of their lone pairs to the carbon of the polarized carbonyl functionality, albeit from an aldehyde or a ketone. So let's take a little more closer look at that. And let's go to the top of page 125, where we discuss the relative reactivities of aldehydes and ketones. And we're going to look at aldehydes first. Now, aldehydes have a tendency, okay, to be more reactive, okay, than ketones. They're more reactive, and the reason for that, they're less hindered, and that should be apparent because we have a hydrogen here versus the carbon. But there's also a greater deal of carbonyl polarization, okay? It's a more polar bond, typically, with aldehydes than you would have with, say, for example, a ketone. Now, we said relative reactivity, so that means something is more reactive than something else, or something's less reactive than something else. What do you notice in common here? Both of these are benzaldehyde derivatives, right? But what's distinct about them is what the group that you have here at the para position, okay? Now, you have to think back again to chapter 16 about what these groups represent and how they behave chemically. Recall that this group here, because it has these lone pairs, okay, it doesn't have to have a lone pair there, but in this case it does. These are what? These are electron releasing groups, ERG, okay? And so we contrast that with something like nitro, which you've learned is one of the more powerful electron withdrawing groups. So this one forces electron density into the ring. This one pulls electron density away from the ring. Now, for electrophilic aromatic substitution, they do one thing, but their behavior towards branching groups is pretty profound. So what if we have this generic nucleophile, okay? In other words, let me just write the word NU. or the symbol NU, and put a lone pair on it. And if we want it to be a charged nucleophile, we could say it's negative. You get the idea. So what if we had both of these in a flask together? Okay, you had the para-methoxybenzaldehyde in a flask, and you also had para-nitrobenzaldehyde. They were dissolved up in a solvent. And you were the nucleophile. Who would you go after first? Would you attack this one, or would you attack this one? It all has to do with which carbonyl is more polarized, okay? And so if you go over here to the left-hand side, we said that electron releasing groups kind of force electron density into the ring, right? Well, that's felt all the way over here, okay? So while this carbon's delta plus, in a relative sense, it would be less delta plus, okay? Same thing. On this side, this electron withdrawing, and that influence is felt all the way over here in the pair position. So what do you know about this carbon? This carbon would be what? In a relative way of speaking, it's more delta plus. So there's a distinction between the carbonyl polarization. So if you're a nucleophile, preferentially, you're going to go after the one with the nitro group. Okay, you're going to form a bond there. So this was something that you kind of learned before, but now you're seeing it in the sense whereby a nucleophile would selectively attack a carbonyl, despite the fact that these groups are so far away on the basis of their electronic characters. Now let's take a look at that kind of thing a little more closely. Let's go to section 19.5 and talk about nucleophilic addition of water. Now remember, just on the previous page we said that water can behave as a nucleophile, and the reason it can behave as a nucleophile is why? Because it has a very electronegative oxygen, but it has those lone pairs. So all that you need is that one lone pair in order to act as a nucleophile. Okay, I'm going to say a few things here, and then we'll kind of reinforce all these concepts as we go through them on a case-by-case basis. Aldehydes and ketones, they produce something known as gem diols. Okay? A gem diol simply means that both the OHs are going to be bonded to the same carbon. We typically call those hydrates. Okay, hence the word hydration. Right? So the water molecules aren't going to be water clinging to like a metal or something y'all saw in general chemistry. These are going to be a little different. Now these reactions are reversible, okay, and they can be done by, we can reverse them by following Le Chatelier's principle, by heating them up, cooling them down, so on and so forth. But I want you to make this distinction here because we're going to look at examples. Ketones tend to be reactant favored. In other words, you're going to kind of favor the ketone side, whereas aldehydes tend to be product favored. They'll favor the hydrate side. And while acids and bases can speed up these reactions, and we'll see examples of that later, they really do not affect the position of the equilibrium. You reach a point where the percentage of hydrate and or non-hydrated species is a constant. So let's contrast these two reactions because they look very much alike, but they could be very, very different. This is acetone, an example of what? A ketone, right? And what are you doing? You're adding water. So you take some acetone, simply mix it with water. And folks, these are infinitely soluble in one another. What do we have here? This is an aldehyde. What are we doing here? Same thing. We're mixing it with water. Okay, and again, these are infinitely soluble. Now, one of these, though, tends to be reactant favored, whereas the other tends to be what? Product favored. Folks, the ketones reactant favored. Hence, that's why the equilibrium arrows are like this, and they're favored to the left. And so you form very little hydrate, okay? Very little, like 0.1%. Okay, that's not much of the hydrate. And again, a hydrate, folks, you can spot those because they're going to have OHs, two of them bonded to the same sp3 carbon. That's what makes a hydrate. Okay? And we can call them gem diols as well. Aldehydes, on the other hand, they're different. Okay. They tend to be product favored. So here, we're actually going to move in the direction of the hydrate. So you've often heard that formaldehyde is used as a biological preservative. Well, it turns out formaldehyde is actually a gas. Okay, and yes, you can smell it, but when you mix it with water, it forms formaldehyde hydrate. And this is actually the biological preservative. So here, there's only about 0.1% of that left over. So henceforth, we can say that the aldehydes are product favored. Okay? Because, in effect, this carbon here is far less hindered. Okay? And this means that this system is more polar. So in the case of water acting as a nucleophile, what's going on there? Okay, the water will simply come in, okay, form a bond here, and then you have a proton scramble about, you get your formaldehyde hydrate. And in the contemporary world, this is known as formalin, okay, formalin. And you can buy that as a biological preservative. Now let's take a look at an example of this reaction. And by looking at sample problem 19.06 at the bottom of page 125. This is called trichloroacetaldehyde, okay? And of course here we have water. It says show the structure of this hydrate. Let's do the structure first, and then I want to go back and kind of explain why this reaction is so product favored. You already know that aldehydes are product favored, right? We know that. We just said that here. But this one is especially product favored. So the trichloromethyl group is there. There it is. Okay. Here's the oxygen. There's the hydrogen you have. And what did you add? What did we add? Water. Okay. So water formed an OH here. Okay, and we get a proton there. So you hardly see the color difference, but folks, this would be our product. And so this would be the structure of the hydrate. Now, how did it happen again? Well, we know that we need a mechanism, right? And without going through all the details of the mechanism, let's just be mindful that water acts as a nucleophile towards this carbonyl. So it'll come in here, like we said before, form a bond, okay? And you end up with your hydrate. But folks, this is an especially good reaction, okay? Because what did we say about this carbonyl? We said it was highly polarized, right? But this was extremely polarized. Why? Why would it be so polarized? The reason it's so polarized is because look at this group here, okay? This is a very powerful electron withdrawing group. So let me write it out condensed. Here's that carbon, here's the 3 chlorines, right? So on and so forth. Like that. We said this is an electron withdrawing group, so it pulls electron density towards itself, and when it does that, it increases the positive character of this carbon here. So anytime you have electron withdrawing groups, okay, attached to aldehyde, even if it's directly attacked, or we saw up here, if it's, even a pair position, that's going to increase the reactivity of the nucleophile attacking the carbonyl so that you form a hydrate. Now, this is also called a Mickey Finn. Don't memorize this, okay? A Mickey Finn comes from old gangster movies, whereby what they would do is they would put this stuff in someone's drink, and then what would happen, they would pass out, and the next day they would wake up at the bottom of the ocean with concrete boots. All right. That's another topic for another day. Let's keep talking about these kind of reactions, though, because they're pretty cool. I want to segue to section 19.6 on page 126, and we'll start looking at the nucleophilic addition of HCN. Okay, HCN is hydrocyanic acid. Some people call it hydrogen cyanide, and yes, it's poisonous, very poisonous, but it makes a really good reactive substrate if you handle it with care. So let me give you a few ideas of what's happening, then we'll talk about how this works. Aldehydes, okay, we know what those are, and unhindered ketones, okay? In other words, these are ketones that don't have a lot of bulk around them, will give us something called a cyanohydrin. Okay, so an example of a cyanohydrin is right there. The cyano part is that's why it's called cyanohydrin, because you have an OH. Both are bonded to an sp3 carbon. So a generic reaction here would be to take an aldehyde. There it is. And then hydrogen cyanide or hydrocyanic acid. Okay. and those form a cyanohydrin. And we'll look at the mechanism here in a little bit. You go ahead and write that name in. Hydro, okay, cyanic acid. Hydrocyanic acid, or you can call it hydrogen cyanide. Folks, if you've ever roasted almonds, and that's okay, maybe around the holidays or whenever, or maybe you smell roasting, maybe you didn't do the roasting, maybe you smell them. What you're smelling is that, okay? Wonderful smell. And so dilute, it's not poisonous, but at very high concentrations, it's extremely poisonous because this group here will bond irreversibly to the iron in hemoglobin, therefore you would not oxygenate your cells. Again, another topic for another day. So here's a specific example, okay, where we're going to take a benzaldehyde. And look what happens. Okay, we end up with this cyanohydrin. So this is an example of an addition reaction. You're going to add these together. This is an addition reaction, okay? No leftover atoms. Now, when McMurray shows you that, he has equilibrium arrows there. And to favor the equilibrium, there's several ways. Number one, you can remove this as its form, have it precipitate out of solution, or you can use a huge excess of DAP. So don't overly concern yourself with this. Typically, I'll just show you an arrow going that way, which means that we're dealing with this in a pragmatic way so that we're producing the corresponding cyanohydrin. So this is Mandel-nitrile. Okay, cyanohydrin. It's a very useful compound to make other things. Those other things we're going to explore in the next pages. Now, none of this would be complete if we don't look at a mechanism, okay? So it says treatment of acetone with hydrocyanic acid and trace amount of sodium cyanide, okay, provides the indicated cyanohydrin. Generally, this kind of kickstarts it, having a little bit of that in there, okay? Let me just kind of write out why that might be the case. You have sodium cation, you have cyanide anion, all right? And a little bit of that will help really kickstart and force that equilibrium to the right. But we don't need that to solve our mechanism. We just need to understand how the mechanism works. Let's take a look at that. Okay, so we're trying to explain how do we go from acetone, hydrocyanic acid, to this particular cyanohydrin, 2-hydroxy-2-methylpropionitrile. Don't worry about the nomenclature of cyanohydrins. We're not going to be tested over that. Well, I think you've seen this kind of thing before. Okay. We know that acids oftentimes function as catalysts. So, and the way they do that is behaving as a Bronsted-Lowry acids. So the one of the lone pairs will act as a Bronsted-Lowry base and pick up a proton from there. Even though it's a weak acid, it can pick up just enough, and you can have a system established where it's going to keep moving in the direction of products. So we're going to set up an equilibrium here between these two. Let's take a look at that. All right, so these methyl groups are intact just like they always were. Nothing's going to happen down there. But now we have a carbonyl, but that carbonyl is suddenly extremely reactive, way more than it was before because you've protonated the oxygen, okay, which makes this carbon way more electrophilic than it was before. Well, what do electrophiles need? They need nucleophiles, don't they? So the nucleophile came about as a consequence of liberating the proton from the hydrocyanic acid. Okay? And so a little bit of, like I said, sodium cyanide in there will kind of help you get the equilibrium in favor of this dissociating into the respective reactive components. Okay, so what do we have? We have ourselves an electrophile on the left, okay, and we have a nucleophile here on the right. Remember that, how that worked? This was a nucleophile, that's an electrophile. The electrophile becomes a nucleophile and vice versa. So nucleophiles do what they do best. By convention, we show them attacking, okay? In this case, it attacked the carbon, and the pi bond becomes a lone pair. And if you follow that rationale, okay, it takes you directly to this product. So this is one of the simpler mechanisms that you'll ever see. Very easy reaction to do in the laboratory, okay? And again, these reactions are very useful for making cyanohydrins. So you need to be able to spot a cyanohydrin. You got an OH there, which makes it hydrin. You have a cyano group there, which makes it cyano. Why do we make them? What are they good for? Well, we're going to take them and convert them into amino alcohols. Now, you had amino alcohols in earlier chapter. Only there you were looking at amines, ammonia, primary amines, secondary amines, attacking what? Epoxides. Well, this is another way to do it. Okay? And you can make all kinds of amino alcohols. So let me highlight the bullet point here. Cyanohydrins may be what? Reduced to amino alcohols. Okay? They may be reduced to amino alcohols. So in effect, we're going to go from here, okay, to there. In other words, a cyanohydrin all the way to an amino alcohol. Now, what's an amino alcohol? What are they? Amino alcohols are characterized by having sp3 carbons with OH on one, okay, and an amino group on the other. In this case, it's going to be an NH2. Okay, so henceforth, this is the generic structure of an amino alcohol. And so the cyanohydrin provided the atoms necessary to do that. Okay, so we have to do a reduction. Now, in order to carry out a reduction, we're going to use a very powerful reducing agent. Okay, and the choice reducing agent here is that one. You've seen it before. This is lithium aluminum hydride. This is a very powerful reducing agent. Okay, so let's just take a look at this again. On the left-hand side, we have what? A cyanohydrin. And on the right-hand side, what do we have? An amino alcohol. Now, amino alcohols themselves can be converted, some of them, to amino acids. Right? So if you ever study biochemistry, you'll learn a little bit about that, amino acids. Now, without going into too much detail with how this works, I would like to give you sort of a generic perspective on what's going on here. Recall that lithium aluminum hydride is a reducing agent, and therefore it's a source of hydride anion. Well, why is that important? As it turns out, two of the hydrogens, okay, one of the carbon and one of the nitrogen come from lithium aluminum hydride. I just indiscriminately chose those two, but one from the carbon, one on the nitrogen comes from step one. What was step one? Addition of lithium aluminum hydride. Okay. And where do the other protons come from? Okay, notice I said this time protons. Okay. In which case it would be these two, that one and that one. Okay, those two come from step two, right? Okay, those two come from step two. Let's squeeze an arrow in there. And that was when you quench with water, okay? And you can also quench with acid. Fact is, if I were doing this in lab, I would probably have my pH a little bit lower than water. It makes the reaction go a little better. So overall, what have you done? What have you done overall? You added 4 hydrogens, okay? So in effect, these two steps do what? They add 4 H's, okay? So no longer are there any pi bonds left. There's 2 pi bonds are completely reduced. We all have nothing but single bonds now. So what's your job? Okay, what do you need to know? What's your primary responsibility as a student? Mostly I would want you to be able, okay, if this were an empty box, to fill it in, okay? And so how do I go about filling that in? Well, first off, you have to recognize that it's incumbent upon you what you're dealing with. You have, okay, a cyanohydrin, okay? But really, it's only this part of the molecule that anything is taking place, okay? What do you need to do? You need to completely break, okay, those pi bonds and replace each and every one of them with hydrogens. So you're going to install hydrogen on this carbon, you're going to install hydrogen on that nitrogen. Okay, and remember, that's where the lithium hydride is important, because it does that. And then you get this point in the reaction where you have to quench it with water and or acid. Water is an acid, by the way, in this case, but you would add hydrogens there as well. So the pi bonds are gone, and therefore you've changed the molecular formula by adding 4 hydrogens. If you do the molecular formula over here, okay, add up all the carbons and hydrogens. Okay, let's just do that. We have 6 carbons here, 7, 8. We have what? C8. Okay, let's count the hydrogens. You have 5 on the ring, 6, 7, 8, 7. Okay. What else do we have? We have an O and a nitrogen, NO. Right, so that's the molecular formula of mandelonitrile. Let's move over here. Here, there's our 6 carbons, 7, 8. Number of carbons hasn't changed, right? Number of nitrogens changed? Nope. Number of oxygens? Nope. What about hydrogen? You already know it should be 9, right? Because we know it should be, what, 7 plus, it should be 11. Let's count them. 5 here, 6, 7, 8, 9, 10, 11. Yep, 11. So C8H11NO. So it's really easy to figure out the molecular formula here because you know you're adding a total of 4 hydrogens. All right. A little bit sloppy. That's C8H11NO. Okay? Let me write it out again. C8H11NO. Okay? So that would be your molecular formula. What's the difference? You added 4 hydrogens. 2 from there, 2 from here. Okay. Now, is there anything else we can do with the cyanohydrin? The answer is yes, there is. Okay. One of the more practical things that can be done with them is cyanohydrins can be hydrolyzed to alpha hydroxycarboxylic acids. Now, the old-fashioned name for that is an acyloin. Okay, acyloin. Right. So an example of an acyloin is that. Now, the reason these are called alpha hydroxy, right, is because if you consider that carbon there as being alpha, it's got a OH group on it, hence alpha hydroxy, and this group over here is a carboxylic acid. Now, it's a very intricate mechanism, but what you're doing is you're simply converting that cyano group into a carboxylic acid, right? And the way you do that is simply by adding acid. Okay, it could be something like sulfuric acid, nitric acid, something like that. And you heat it under reflux for an extended period, quench the reaction and isolate this. So these are very useful compounds for all kinds of applications. So you're going from a nitrile to a carboxylic acid. So here's a specific example. And this kind of goes back to what I want you to be able to do. Okay, in other words, let's presume that there's an empty box here, okay? And you look at the reaction, you see I have a cyanohydride here. I'm sorry, a cyanohydrin. I'm refluxing in an acid, so I need to convert that into a carboxylic acid. Okay? And if you really want to test your mechanism skills, try working that one out. Okay? It's a lot of fun. Now, as you know, the primary task of any organic chemist is, and well should be, the synthesis of organic compounds. So let's try a synthesis here using the reactions that we've discussed up to this point. And after that, I'm going to go kind of quickly because the next set of material you've already seen in chapter 17. So I'll just kind of go through that kind of quickly. All right. At the top of page 128, it says provide a synthesis of 3-cyclohexyl 2-hydroxypropionic acid. In other words, this compound here. From 2-cyclohexyl ethanol in this compound here. Okay? So we need to think back of what's going on here. Right? In other words, kind of get a snapshot of the overall effect. And what I notice at a glance is that here at this carbon, okay, that it corresponds to that carbon. So in effect, we need to add or install that carboxylic acid group at that position. Now there's no reagent that can do that. Okay, there isn't. But we can conduct a series of reactions in order to influence this overall process. So at the bottom of page 127, we said that these were called acetaloins, or alpha hydroxycarboxylic acid. So here's my alpha carbon. The alpha carbon bears an OH, and it has a carboxylic acid. Well, how do you make those? Let's just work backwards. Okay, how do you make those? Didn't we say that you had to start with the corresponding cyanohydrin? What would the corresponding cyanohydrin look like? What would it look like? This is what it would look like. Okay. You've got your OH here, and you've got your cyano group here. Now I'm going to write the cyano out showing the bond, but you could just write CN if you wanted to. And now go ahead and sketch that hydrogen in, why not? So if we had this compound somewhere along the way, then we know that all that we would have to do is subject this compound to a Bronsted acid, okay, and heat it under reflux, and then ultimately we would get that desired product. Well, is there a way to go from here to here? The answer, not directly, but there is a two-step process. Think back, a couple pages back, how did we make cyanohydrins? Okay, in other words, this is a cyanohydrin, right? How do we make those? You make them by adding what? Hydrogen cyanide or hydrocyanic acid to what? An aldehyde or a ketone. In this case, we would know we would need an aldehyde because we see a hydrogen there. So it's simply a question of installing this group into the corresponding aldehyde. And what does the corresponding aldehyde look like? The corresponding aldehyde would have this structure. Okay? Plain and simple. That structure. This is your aldehyde. And how do we do this? It's an equilibrium process, but remember I told you, just you can have a reaction arrow here. Okay? And stoichiometrically, we would probably add a huge excess of that to force the equilibrium to the cyanohydrin. That might be one way to do it. But how do we go from this to here? See how we're working backwards? Well, what kind of alcohol is this? This is a primary alcohol, right? And what is this? This is an aldehyde. Haven't we learned ways to do that? There's two ways to do that. The way that you learned back in chapter 17, and it was repeated here in chapter 19, was to use the Des-Martin per iodinine. Okay? Des-Martin. And I'm just going to write Des-Martin. Okay? But we also learned in the chapter that you could use pyridinium chlorochromate. But if you do that, make sure you have this solvent, dichloromethane, shown. And interestingly, the Des-Martin also uses dichloromethane, but you don't really have to use dichloromethane with Des-Martin. You just do there. So this would be the overall process. Okay, so how many steps were involved in converting this to this? The answer is 1, 2, 3. All right, so take a look at this synthesis. I think it's a good one for you to review. It kind of summarizes what we've learned in this chapter, and it's just a good problem, just a really good problem. And by the way, folks, this species, okay, alpha hydroxy carboxylic acid, common name is an acetaloin. All right, that's the old-fashioned name, acetaloin. All right, kind of a weird sounding name, but nonetheless, that's what they used to call these things. In many cases, we still do. All right, middle of page 128. Folks, the next several pages are things that you've already seen before in chapter 17. Okay, so I'm going to kind of just go through this really quickly and just remind you of this. If you want to fast forward, feel free to do that. A little bit of this will appear on your next exam and also on the final, but you've already seen it, so we probably need not to dwell upon this. But again, this is the perfect topic for this chapter. We're talking about the nucleophilic addition of hydride, okay, and Grignard reagents. Now, a Grignard reagent is what? The source of the carbanion ion, okay? And in this case, we're going to produce alcohols. So this turned out to be very important. Okay, Victor Grignard won the Nobel Prize. We learned that Grignard reagents behave like as if they were salts with a nucleophilic carbanion, and that's what attacks your
your electrophilic carbonyl. We've learned that Grignard plus aldehydes give us secondary alcohols, and we also learned that Grignards plus ketones give us tertiary alcohols, and Grignard plus esters give you tertiary alcohols too. So here was a specific example of that, okay, where we went from benzaldehyde to 1-phenylethanol. This is an example of going from an aldehyde to a secondary alcohol by choice of Grignard. And let's go to page 129. Something I had said also and talked about earlier, Grignard plus a ketone gives you a tertiary alcohol. So here we have acetophenone. We're adding methyl magnesium bromide, and we're getting this tertiary alcohol as a consequence of this process. Okay. Mechanistically speaking, the Grignard, okay, kind of forms a complex, but it makes a very reactive complex with the metal component of the Grignard reagent, okay, forming a bond. So we have this magnesium oxygen bond, and fairly polarized bond. And remember I talked about the trajectory of the nucleophile? It kind of sits over here, but this carbon now, guys, is extremely reactive now because it's the oxygen adjacent to it increases the polarity of the delta positive nature of this carbon. So the carbanion would act as a nucleophile here, and one of the pi bonds would form a lone pair to that oxygen, and you get this thing here called an alkoxide intermediate. Alkoxide intermediate. And then you would add water, and usually we don't add water, we add something like ammonium chloride or something to have the pH far less than 7, and then that would actually convert the alkoxide into corresponding alcohol. I'm brokenhearted we couldn't do this reaction in lab, guys. This was going to be a lot of fun, and you were going to see that stuff form in the aqueous layer. Grignard reaction. Okay, so let me just do one example. Now remember, if you have a tertiary alcohol, okay, there's 3 ways to do it. If you have 3 different R groups, you have a propyl, a methyl, and an ethyl. So that means there's 3 different ways to make this particular tertiary alcohols using Grignard chemistry. All right. So top of the page, we said a Grignard plus a ketone gives you a tertiary alcohol, so we just need to figure out a ketone, and of course we need a Grignard inside this box that I have with the ether next to it. So several approaches. Okay, I'm just going to do this one approach. I'm going to find a carbon chain. Okay, there's one, but I'm going to take a detour like that. So we end up with what size of carbon chain? 1, 2, 3, 4, 5 carbon chain. So I need a 5 carbon chain. All right. So let me just go ahead and draw it kind of like we see it over there using this condensed illustration. So here's the carbon that bears the oxygen, and there would be the methyl like that. Okay, and this is what now? It's the carbonyl. So 1, 2, 3, 4, 5. This is 2-pentanone. So in order to conduct this appropriately, we need a Grignard reagent that contains 2 carbons. So we use the ethyl component. So let me just write that in. This is ethyl. And notice the order I'm going here. Ethyl, and then we need magnesium in the middle and bromine on the end. Okay, so this is called ethyl magnesium bromide, and we have an ethereal solvent. Okay, this could be diethyl ether. It could also be tetrahydrofuran. Now, the proton that you're looking at here, okay, that one, okay, that proton came from step 2 with the addition of aqueous ammonium chloride. Okay, so this is from step 2. That's why it's important that we quench with an acid, because we need to liberate that alkoxide from the magnesium. So this was from step 2. So this is just one of 3 ways to make that tertiary alcohol using Grignard chemistry. Now on page 130, I have all 3 approaches. You may recognize this. These are 3 different approaches that all of them result in the same product. Okay, so take a look at those as a reminder for how to do this Grignard chemistry. Okay, but in all cases we have ketones, and they're all different. In all cases we have
Grignard reagents, which also are all different. So give this a look-see so that you can kind of get a perspective on how all of this works. Now, let's go a little bit further, and this again is a review. The reduction of carbonyls to alcohols. This turned out to be some relatively simple chemistry as well. So we're going in the opposite direction now. We're going to reduce an aldehyde and or a ketone to its corresponding alcohol. So what goes on here? You may remember that aldehydes can be reduced to primary alcohols using sodium borohydride. Okay, so this is an aldehyde, benzaldehyde. This is our reducing agent. Okay, now the reducing agent is a source of hydride anion. And what will that hydride anion do? It will attack, okay, to the carbon. So this carbon already had hydrogen on it, so I'm going to highlight that in yellow. And where did that other hydrogen, so to speak, come from? Okay, the one I'm going to highlight in blue. Okay, that came from the reducing agent, in this case hydride. And then finally, the proton that you see here, kind of like the one we just saw with the Grignard, okay, but these are very much alike. That proton that you placed there on the alkoxide comes from step 2. So a person could use water, okay, or you could use ammonium chloride, some source of a Bronsted-Lowry acid. And similarly, guys, again, this is a review, we can reduce a carbonyl. In this case, we have a ketone using the same set of reagents, sodium borohydride, ethanol. And so if you go from a ketone, we're going to end up with a secondary alcohol. All right, so this is an example of that. All right, so this is pretty much a review, these last several pages of things that you had back in chapter 17 when we talked about alcohol. So I think this is a good place to stop again, and then we're going to pick up with the new material for this really lengthy chapter in the next few moments. I'll talk to you guys later.